Καλησπέρα σε όλους. So, good afternoon, everybody. I think the support take place in English. So, it's the first seminar of the new academic year. I'm Scarmeas, and together with Takis Lamos, we are co-hosting this first seminar. So, I will start. We're a little bit a few minutes late, so I think it's a good idea if we start by introducing today's speakers. So we will start. First of all, let's start with the title. So the title of today's presentation will be Application of Artificial Intelligence Techniques in HELIAD Data. The hope is to show some preliminary results. So it's a collaboration between the National Kapodistrian University of Athens and Ionian University. So we have 4 speakers. We will start with E.Ntanasi. Eva is a researcher, postdoc at the National and Kapodistrian University of Athens, working with me at the Aiginition Hospital. And she will make a brief introduction describing the epidemiological study that provided the data for the further analysis. And then we have 3 presenters from Ionian University, the Department of Informatics. So we have G.Dimakopoulos, who's a researcher, and then Aris, A.Vrahatis, and Themis, Exarchos, who are both faculty at Ionian University. So I think without further delay, I think we can proceed to the presentation. You want to start?
Yes. First of all, we would like all to thank you for giving us the opportunity to share with you these preliminary results from our research on how artificial intelligence techniques can be used in order to identify markers of dementia and cognitive decline. In the title of today's presentation, we refer to HELIAD study, and thus I would like to introduce you to some brief information regarding HELIAD. So HELIAD is a population-based study that was designed to estimate the prevalence and incidence of Alzheimer's disease, other dementias, mild cognitive impairment, and other neuropsychiatric conditions of the aging population. It also aims to investigate the role that lifestyle and genetic factors could possibly have on cognition and healthy aging. As far as the sample of HELIAD is concerned, we have people above the age of 65 years old who were randomly selected from the municipality registries of 2 cities, the city of Marousi, which is a suburb of Athens, and the city of Larissa. Until now, we have 2,000 participants that have completed the baseline assessment and almost 1,100 participants that have completed the first follow-up. We have a second follow-up that is ongoing, and it will be completed by the end of the next year. So HELIAD participants are re-evaluated almost every 3 years. The data gathered in HELIAD include, among other, demographic characteristics, information about early life events and socioeconomic status. We also gather clinical information about the medical neurological conditions of participants, their family history, and the use of the current medication use. All participants undergo an extensive neuropsychological evaluation. I will refer to this in the next slides. And they also answer on detailed questionnaires about their participation on mental, physical, occupational, and social activities. They also report any memory or other subjective cognitive complaints that they may have, and they complete also questionnaires about their everyday functioning, their motor functioning, their sleep and nutrition. Moreover, in this study, all participants undergo a structured physical examination. So the neurologists that participate as researchers in the study carry out a neurological evaluation and document all the neurological findings from the participants. They also administer some scales that we can see in this slide that provide clinical information about the presence of cognitive impairment or dementia, about movement disorders and psychiatric symptoms. And now all this data from the neurological evaluation, the neuropsychological evaluation and the clinical scales are gathered and are reviewed at some expert consensus meetings. In these meetings participate the neurologists, neuropsychologists, and other researchers that are involved in the HELIAD project, and they conclude to participants' diagnosis. And all diagnoses are made according to established criteria. As I mentioned before, all participants also have completed a detailed neuropsychological evaluation. And in this table, we tried to summarize the cognitive domains that are assessed in a HELIAD study, and also the specific cognitive tests that we have used. You can see that except from the global cognition, we also assess the domains of attention and speed, executive functioning, memory, visual-perceptual ability, and language. And we use participants' performance on these tests, and we take this performance into account when we set their diagnosis. But we also use these tests and the scores on these tests as a measurement of participants' cognition. So to do that, we convert participants' raw scores on each cognitive test into z-scores. And so for each cognitive test that you saw in the previous table, we have a separate z-score. And these individual z-scores are then grouped based on the cognitive domain that they assess. And we have created some average composite score for each cognitive domain. In other words, for example, we have the z-scores from different tests that assess memory. And we group these z-scores and we produce an average z-score for memory. And we have done that also for the domain of language, for attention speed, executive function, and visuospatial function. So from all these z-scores that we had originally, we ended up with 5 main composite scores that refer to each cognitive domain. And we also averaged these 5 domain composite scores into a global z-score which measures the global cognition of participants. So doing so, we have also a metric, quantitative measurement of cognition for our participants. I will stop here with the presentation of the HELIAD, of the brief presentation, and George will continue with how artificial intelligence was used in this data.
Hello, good afternoon. Thank you, Eva. Thanks a lot. I'm going straight to the concept. Now we focus on 2 critical keywords of Alzheimer's disease. It's the early and accurate diagnosis. A secure way to achieve early and accurate diagnosis is to identify that specific subset of biomarkers, also called predictors, that are strongly correlated with diagnosis, called target or outcome variable, even at the early stages of the disease. Then we use AI techniques and make accurate prediction on new and unseen data. The objective, we can start with a question. So what is the benefit of using machine learning on HELIAD data sets? So using machine learning, which is an area, a wide area of artificial intelligence, we can predict with confidence the 3 levels of diagnosis, the MCI, Alzheimer, or control, on new and unseen observation using only the most relevant subset of biomarkers. This subset of feature has been successfully identified during feature selection task found in model training phase, which discussed later. So the methods, we can say that there is a life cycle from data collection to model deployment. There are many phases, many pillars within. There are various phases and pipelines in between required to bring the data sets in a form that is recognized by machine learning algorithms so can make predictions with accuracy on new and unseen data. So for the data pre-processing, which is the next slide, which is also called data preparation in machine learning project, is more than 80% of the project time, which is quite huge, the time we spend on data preparation. It is the most important, however, it's the most important phase because it is the act of transforming raw data into a form that is appropriate for modeling. Okay, for instance, machine learning algorithms requires input to be numbers. So if data contains other data types apart from numbers, such as labels, we need to convert, to change the data into numbers. Moreover, specific machine learning algorithms have expectations regarding the data types, the scale of input variables. We have the same scale, for instance, for the balance, the probability distribution. Maybe they need more Gaussian distribution, the relationship between variables, or the no relationship between variables, and so on. Now, regarding the data collection, and in particular for the data for the HELIAD dataset, we examine as part of data science approximately 2 case samples, which is the row of the dataset. We also approximately we examined 1.1K features, which is the columns or the predictors in the dataset. And for an outcome, we had 1 category target class with 3 labels prepared for classification modeling. So for the pre-processing, for the pipeline in data pre-processing, there are many different statistical analysis and data visualization techniques to explore data set. It's very important, very crucial to explore the data set before applying any model, any algorithm. We need to capture and understand the domain. In particular, we need to identify the data cleaning operation, which is very important step also. Some very basic data cleaning operations are, for instance, how to identify and remove columns that have only a single value. They don't give any more value, any added value to the model. Also, we need to identify and consider columns with very few unique values. It's more or less the same thing. How to identify and remove rows with duplicate observations, or remove columns that have a low variance. Identify outliers, for instance, or identify missing values, or empty values, etc. So all of these phases, all of these tasks are part of the data cleaning. So as an outcome, we went through all this pre-processing for the HELIAD dataset. And after finishing the data preparation phase, the input variables in the resulting dataset were reduced by 44% and also identifying 23% observation with outliers. So removing them, we improve in this way the prediction accuracy by removing also noisy data, and removing or imputing missing or empty data. So for splitting in machine learning process, before deploying a selected model, we need first to train the model. It's a very crucial phase in machine learning. And we train the model with a data set, with a subset of a data, let's say the 80% of the data set, and then evaluate or test the prediction accuracy of selected model by using the rest of the 20% of the data. And we use it as unseen, as new data. All the pre-processing tasks are applied only on training sets, avoiding in such way data leakage or bias that impacts the model prediction accuracy. So in classification model, another very critical and very common issue in data structure is the so-called class imbalance, where we, in this case, we have observations that are not equally balanced between classes. In HELIAD dataset, for instance, we had 88% of samples were classified in control. So we can proceed now with Aris.
Okay, did you hear me? Thank you, George. Thank you to all. Now, given that we have a clean data set, we need a further analysis. A first approach here is to use AI, to use machine learning. Why we need here to use machine learning? We need, since we have a data set with very complex data set with high dimensionality. Note here that our dataset has several hundred of features. That means that we have to deal with a very high dimensionality. Also, AI can deal with huge dimensionality. AI can identify, can export hidden patterns that we cannot observe using a traditional method, a statistical, for example. And also AI offer very strong predictive processes. Now, if we compare AI with traditional statistics, we can see the superiority of AI in terms of adaptability, model variety, in automation and feature selection, to deal with complex relationships with complex data and high-dimensional data. Also, AI has very strong capabilities in prediction tasks, in supervised learning, and also it is very robust to noise, to outliers, and to other issues that make difficult to discriminate our classes in our dataset. Now, go to the next slide, please. Okay, here we see the machine learning, which is under the umbrella of AI. We see all the variety, all the fields of machine learning, such as the supervised and unsupervised learning. Here we'll focus, next slide, we'll focus on the classification and dimensionality reduction. The classification belongs to the category of supervised learning, and dimensionality reduction belongs to the unsupervised learning category. Now, we'll see the first category, the dimensionality reduction. We see that the dimensionality reduction, the concept is to reduce the dimensionality from a very high dimensional space to transform the space to a lower dimensional space, but in parallel to keep all the pairwise distance. Dimensionality reduction benefits are noise reduction to improve the computational efficiency. It enhances the model. We can have a better accuracy by removing the noise and the high dimensionality in a dataset. Okay, here we see our dataset with 1,500 of samples. The dots, the blue dots are MCI, the green dementia, and the red are normal. We see here an imbalanced dataset with most observation very dominant to the normal state. We see a very complex dataset. Note here that we see a dimensionality reducted dataset. We see here 2 dimensions. We convert the 500 dimensions to 2 dimensions. And we see here our results. Also, we can see here are very complex data set and very, very difficult to discriminate these classes. So we need very strong and appropriate machine learning tools in order to hidden the patterns from this dataset in order to discriminate, to find the markers, the digital indicators that discriminate these three classes. Okay, here we apply the RAS-Boost. RAS-Boost is a tree-based algorithm, an ensemble tree-based algorithm. We apply it here on this dataset, on HELIAD dataset. RAS-Boost can manage imbalanced data, as you see before. And also, RAS-Boost is a combination with random undersampling and a boosting algorithm. More details about RAS-Boost, random undersampling boost, developed to address this problem, the problem of imbalanced dataset, and to classify multi-class problems. It uses a combination of data sampling, here is the undersampling, and a boosting approach, and also a bugging approach to improve the classification performance. And the steps are the undersampling. After is the train classifier. It computes an error in the classification. It calculates the classifier weights and also update the weights of this classifier. And then we have the final model. It's a very accurate model when we have to deal with imbalanced data set. And also, you can see in the next slide that we can see the superiority of RAS-Boost. You see the accuracy, specificity, and F1 score in terms of discriminate the three classes, the normal, the MCI, and dementia. And by comparing RAS-Boost using the well-established random forest, which is a tree-based classifier, the KNN, a classifier, very well-known traditional classifier, which is based on neighborhoods, and a linear classifier such as SVM, the support vector machines, another traditional classifier. So we can see here the confusion matrix of and the prediction accuracy of RAS-Boost. We can see that even we have a very difficult, very complex data, we can achieve a very good performance using the appropriate algorithm. In each case is RAS-Boost. So Themis, is your turn, I think? Okay.
Yes, thank you. So in this slide, you can see a decision tree, a tree that as outcome of the RAS-Boost algorithm that was created, applied on the HELIAD data. You see the basic structure that starts from a root node, which is essentially the most important and informative features during prediction. They are rather coded here based on the HELIAD initial data. However, we have the information what is what. So the algorithm develops a tree-based structure, which is essential as it can provide also interpretation for the final decisions made. So a clinician can use this tree classifier in order to infer new data, providing also the necessary prediction, the necessary interpretation, why the outcome is this, or why you classify this patient as potential MCI or potential Alzheimer, because you can follow traverse the tree from the root to the leaves and identify the path that leads to this decision. And another important step that takes place during the process is the identification of dominant or informative features. And we calculate the variable importance in tree-based classifiers, which is a measure that is used to quantify the significance of each feature in the prediction process. The features are ranked based on their importance measures, and those with higher values are deemed more significant in the prediction process. Those with lower values are usually eliminated from the prediction model and are not used further on. This can also enhance the interpretability and the explainability of the models derived. It helps understanding which features are driving predictions. And in high-dimensional data sets, it can be used to identify and retain only the most important ones. So this has another outcome that if this is validated also, if these informative features are validated by the people that are collecting data, in the next collection, in the next point, or in the next collection of data, those features maybe can be omitted from being collected from the patients. And by eliminating non-informative features, model can become more accurate and less prone to overfitting. You can see in the lower side of the slide how we can initially have a full feature set. Some useful features are identified, and the rest are removed from the prediction models. Here is a sample of one of the experiments performed during the application of the AI techniques in HELIAD study. You see some of the dominant features that have been retained and strongly correlated with the outcome of diagnosis into healthy controls, MCI, and Alzheimer's. So you see, for example, you have several CDR related features. Some other also are regarding problems going outside by himself because of memory loss, some telephone users. There are also others. You see here some of those that have been retained in the top as being the most informative. And then we visualize in box plots those dominant features. You see, for example, on the left side is the CDR memory, in the middle is the CDR judgment and problem solving, and on the right-hand side is the community affairs, showing, not very clearly, but showing that these features have some discrimination ability higher than the other features that have been removed. Also here for orientation, home and hobbies, and personal care. Now, concluding this analysis, what we propose is early and accurate diagnosis for helping the disease management and therapeutic outcomes. The objective achieved is that we aim to discern a subset of biomarkers and features and clinical characteristics that can classify participants into control, MCI, and dementia categories, effectively as seen by the results. I would like to report again here that usually in such highly unbalanced data, it's very difficult to achieve such big accuracy and sensitivity numbers, especially for the lower ranked category. AI methodologies, and specifically the tree-based classifiers, have been proved to be a valuable tool in accurately predicting the clinical diagnosis, and further that provide interpretation and explainability for the decisions made. Something which in the clinical domain is very important. Our model successfully classified the neurological patients with MCI, dementia, and Alzheimer's Alzheimer and health controls with an overall accuracy in all three categories of exceeding 85%. And the final dataset used, the initial dataset used, had 1,127 predictors, and our model managed to identify those the most informative ones. So we reduced initially the dataset, the predictors, to 500 by removing low variance data or data with very missing values. But then, in order to reduce from 500 to approximately 80 predictors, we used these sophisticated techniques that showed a great correlation with the target outcome. Through variable importance, we have presented the 15 dominant predictors most influential in the classification task. This has a direct impact on clinical practices that streamline the set of biomarkers, can simplify and expedite the diagnostic procedures in the clinical settings, leading to faster and more efficient patient management. While our results are promising, further validation is needed in different and other real-world clinical data sets in order to see the findings' applicability. This research helps bridge the gap between the vast complexity of Alzheimer's biomarkers and practical diagnostic procedures, making early detection more accessible. And finally, the integration of AI in medical diagnosis, as evidenced by our study, paves the way for a more precise, timely, and data-driven decision-making. that can be used in neurodegenerative diseases. Concluding also, this was a preliminary analysis of the HELIAD data, of the HELIAD data set. Only one time point was used. However, we have already started working using the second and the third the first and the second follow-ups in order to come up with much more useful prediction models that can predict a future diagnosis based on a baseline examination. What we presented today is part of a publication entitled Application of Machine Learning Techniques in the HELIAD Study, Data for the Development of Diagnostic Models in MCI and Dementia. It has been presented during the recent Genedis conference, and very recently, a couple of days ago, it has been published in the Advances in Experimental Medicine and Biology of Springer Nature. Thank you.
So I would like to thank everybody, all four presenters. I think to me it was quite helpful because, you know, being a little bit naive and not experienced with the analysis part, I think I understood a little bit more than I used to be able to understand. So maybe I will start by asking a couple of questions, and then I will ask maybe Takis to continue with the coordination in case people have other questions, because I'm in, you know, I'm on the phone and I'm not able to see very well the whole universe of other participants, and I cannot see very well the questions that might be coming up through the chat. So actually I have two like small clarifications. So I was very impressed by all the data cleaning processing, pre-processing, and you know, from 2,000 lines. Yes, maybe we can try and put the PDF as Kostas asked in the chat box. So from the 2,000 you know, participants and almost a similar number of variables, I think we went down to something less than 500. So it's an impressive process. So I think we're lucky that we had so many data so that we'll be able to work with only a fraction of them at the end. So here I have a question for George, for Yorgos. You said that we also eliminate variables with low variability. Does this mean we eliminate Dimakopoulos variables of a 0-1 function, or I misunderstood this? So that's the first question, and the other would be for any one of you. Can you compare a little bit to what is out there in terms of previous literature? I mean, what about other similar studies that have used the same or other similar analytical approaches? Were they more successful than we are? How does what we find compare to what is out there in by previous investigators? Thank you.
Yes, regarding the low variance, and there are some statistical measures that they don't give any more value to the model, meaning that if a column, a variable has a low variance total, meaning that we don't have many differences, many variations between the values, and having this this variable with nearly a constant behaving like a constant, having, I mean, all the values have the same, are the same. This predictor doesn't give any more any added value to the model. So we don't use it, this variable. The model doesn't use this variable anyway. So this is a common process to having a cutoff, a threshold, then having a variance below this threshold. Then we completely remove the predictor.
So just to clarify, you mean that, for example, if we have 60% men, 40% women, we will keep the variable, but if it's 95%, 5%, then we will eliminate it. That's what you're referring to, meaning low variability?
The low variability, yeah, not that is not the 60-40, but maybe the 99%. We have, for instance, 95 and 99% with the same value. then maybe yes, this column may be picked to be removed.
Okay, thanks.
Can I answer to the second question?
Yeah, of course.
Okay, regarding the similar works in the literature, I'm not sure if it's if we've changed in the YouTube yet. Okay, regarding the similar works in the literature, there are several works applying similar techniques in the ADNI data, the Alzheimer's Disease Neuroimaging Initiative, which is a far bigger cohort. However, the difference, and of course there are other researchers that use their own data, like for example, like HELIAD study for applying similar techniques for diagnostic or prognostic models. However, the advantage and the innovation that is presented here is that first comes from the nature of HELIAD study, which is an observational study, so which is also seen by the number of controls existing there. And this peculiarity of the dataset makes our task much more difficult. That's why we also used very innovative and new algorithms, state-of-the-art algorithms like RusBoost that was presented before, in order to accommodate this problem. So there is innovation both in the data as well as in the techniques.
Yeah, Taki, can you take on in terms of other questions from the audience?
Yes. Professor Liketsos wants to have a question. Yes, Kostas?
Thank you. I'd like to compliment this work. It's very important. Obviously, it's developmental. I will point out that it's very similar to work that Roy Adams is doing at our PMC, and just emphasize that pretty soon the Ionian team will be part of doing this work in the data set of close to 150,000 people. So hopefully we'll be able to have better insights. But I actually make that point because I want to raise the question of sample size. What really changes when you go from 2,000, a similar observational study, to 150,000 in sample size? What can you do more? What is more precise? What are the downsides? Because I believe ultimately these are big data methods for a reason. And while applying to 2,000 people is helpful, I think this is going to be most useful when you're talking hundreds of thousands, if not millions, of individuals in data sets.
If I may say first answer, then maybe others also want to say something. The bigger size and size that big from going from 2,000 to 150,000 is actually what is necessary here in order to confirm if our findings can do what we say, generalize in a much larger population. I don't, and of course the statistical significance of the results is huge then. I don't see any disadvantage. It will be difficult to manage those data in terms of computational complexity and time, but in terms of the quality of the target outcomes, I think is optimum.
Just to stay on that, you're thinking of the larger data set ultimately as a validation data set, which is important. But from the point of view of using a larger data set as a training data set, what would the advantages be?
Could be as a validation, but of course the important thing is to train again using the bigger data. So for example, it would be better to train with a larger data set and test with a smaller amount of data. Having available such enormous amount of data will give us too many options. So besides a diagnostic/prediction model that was proposed here, we could see and analyze many different research questions. So something, for example, that we didn't see here is a correlation between different variables in the different time points, which requires an adequate number of observations and distribution of observation in the different time points in order to be able to provide correlation outcomes. So we can explore thousands of things having such large data sets. We can for example, perform also subgroup analysis. So from the 150,000, we can select a subgroup with a specific profile that, for example, you will choose and perform the analysis only for the specific profile. For example, those that have the genetic variant, or those that have, for example, a range of MMSE that is relevant, that it is something we want to see. So we can do too many things.
Can I ask something here? I don't know, maybe I can paraphrase something that could be on Costa's head or on other people's head. What pays more in terms of these analytic approaches? To have a deeper phenotyping with a smaller number of participants, so have a lot of variables and participants, a smaller amount of information but on a huge number of participants, or it doesn't make sense, or there's no discrete advantage to any of these options?
If you ask us from the technical side, the deeper phenotyping and the larger population is the best. The deeper phenotyping with less patients, it could be somehow problematic because you cannot, what you will have as outcomes cannot be validated in a large population. On the other hand side, the less phenotyping with a bigger population could, identify some things that are already known. So if there is just a screening of many people for MCI and Alzheimer's using basic tests without sophisticated examinations, could come up to some outcomes that are already known in the clinical community.
Also, sorry, Themis, let me add that in machine learning operates better with large data set, but in terms of samples, not in patients, not in terms of feature. When we have to deal with a high-dimensional feature, such in our example, we have 100 of features, we have the issue of Kershaw dimensionality. We have to compute distance in a very high-dimensional space, so we lost our information. So we need to reduce this complexity in two ways. The one is feature selection, to isolate the most dominant feature. The other way is to transform the space from the high-dimensional to the low-dimensional. Also, in machine learning, it has been shown that when we have to deal with several hundred or thousands of features, for example, transcriptomics or genomics with a lot of whole genome sequencing data with several thousand of information, only few decades of feature are able to discriminate our classes. Now, in our example, we see that even we have thousands of feature, only 10 or 20 feature are able to discriminate our classes in the same performance, in the same accuracy. So this is very crucial when we have to deal with large data set. So we need large data set, but in the terms of patients, not in the dimensionality.
Yeah, let me touch on Nikos's. I don't know if you're dancing around, but you're starting to put your finger on one of the challenges of large data sets. The provenance of large data sets is what we call real world data. So these are data that are accrued in electronic health records, claims, etc. So they are quite incomplete. Physicians are not researchers, and so what's in the record has a couple of problems: missing this, and then uncertainty about let's say, how the diagnoses are made. Whereas in HELIAD, you have a very standardized, fairly complete data set. So one of the approaches, because you can't get data sets of millions out of research, right? It's just feasible, but you can get them by accruing data from what's already happening in day-to-day practice and recorded in the US in electronic health records. So the ideal solution, we think, is to find the subset of people in your data set of 150,000 people that we have, find the subset of people who have been in research studies related to the topic, so that you can link up and you can see the differences between the way that people are characterized in research at the same time characterized in an electronic health record. Are the diagnoses the same? Are the mean mentals the same? Just to give you a few examples. And that's one solution, but also quite hard to do. Nico is familiar with the ADRC system in the US. There are 40 ADRCs that collect data. There are about 50,000 people who have structured data at this point. That's what we want. We want to link up the ADRC data, which in some ways is like HELIAD, with the electronic health records. And we want to use that link up to learn something about the non-ADRC participants, where we have the more missingness and the more question about the diagnosis. So it's a lengthy exercise.
Okay, do we have another question? Okay, so many thanks to the lectures, to Nikos Scarmeas, to all the attendees. Thank you very much. See you at the next one. Ioannis Sotiropoulos, want to close?
5th of October, okay, 5th of October. Thanks to everybody.
Thank you.
Afternoon.
Bye-bye. It's a pleasure.
Thank everybody. Thanks everybody.
Thank you. Bye.
Thanks, everybody.